In this episode of Fuel Talk, we're going to do a follow-up on the last episode where we discussed what possible failure modes happened to the Crusher Camaro. A lot of it was speculative as we're not sure what exactly happened to it. I didn't have the fuel pump in my hands to see what happened, but we're going to discuss that a little bit further. We also had a comment on the last episode of a request to do a follow-up a little bit more discussing what are some of the misconceptions out there regarding a puller or a pusher pump, and talk about different types of fuel pumps and the effects that may have on both scavenging and cavitation. Here we go. Before we talk about EFI systems, I wanted to break down what other systems existed before that with the carbureted type setup. And back when the Crusher Camaro was first manufactured, it had a pickup system and had a straining filter, as we discussed. This is the diagram that I showed before. Now I don't show the straining filter at the inlet, but it originally had a straining filter to prevent debris from being entered into the fuel system itself. And here's a diagram that I found about to show a cross-section of a mechanical pump that would be a type of pump that would be on vehicles back then for carbureted systems. And here it's a good idea to show because one of the benefits that these old diaphragm systems had was that they are able to scavenge extremely well. And that was a very important characteristic for OEs back then, to make sure that we have fuel continuously to flow. Here it shows the basic structure of the system, in that we have a diaphragm that is pumping back and forth within the chamber there, changing the volume within that chamber. And as the diaphragm allows to the expansion of the fuel within there, this draws in the fuel from the tank into the chamber. The inlet check valve shown here allows fuel to flow into there, but closes when you try to push or create pressure behind it. And the opposite action check valve is for the pump outlet, as shown, such that when you're trying to compress or push on that chamber and reduce its volume inside there, that pushes the fuel into the carburetor, where proper scavenging can happen. On a carburetor, as the fuel enters into the float bowl, as air and other things would go into there, or other pent-up gases or vapors, those can be vented through the vent on a carburetor. And this allows the pump to self-scavenge and have straight fuel available to go through the jets of the carburetor. Now, one of the real advantages to these diaphragm assemblies or type of pumps is that they can pump air and gasoline at efficient rates at a given flow condition. And it doesn't care if it's gas or liquid. And in that characteristic, it becomes very helpful into scavenging the system, being able to draw on the fuel tank to pull out any types of air that might enter into the system, and be able to do that and have self-priming capabilities. These are characteristics that are very important for a carbureted system or any system, but one of the reasons why they certainly don't do that with EFI systems has to deal with the pressure that's required. EFI requires that the fuel is at a given pressure and be free of air, such that when the injector opens, we have a predetermined amount of fuel that will enter into the engine. One of the other disadvantages of a diaphragm system is that you'll have inconsistent pressure. You're going to see huge spikes in pressure as the chamber is closed and pushing fuel into there versus expanding to allow fuel to re-enter the chamber. And these will create huge spikes and huge pressure fluctuations that simply would not affect a carbureted system. So that's why they didn't mind them for a carburetor. If you had the fuel pressure and show it there, we might see that it's pretty consistent on a gauge. However, if you break down over time or slow periods of time and quickly look at what happened to that pressure, you'll find spikes and all kinds of undesired effects that would really reap havoc on an EFI system. So let's take what OEs did for the most part, and this doesn't apply to all OE vehicles, but to most of them. I show a diagram on what that would look like, and I'm mostly highlighting some features that are important. Here we can show that the pump itself, which is typically a turbine pump, and we'll get into those differences in a minute, but it shows where we have a basket feature. This is an attempt to help mitigate sloshing in the pump to prevent air from entering into the fuel system. Before, with a straight pickup system, you cannot control what sloshing can occur. But in this basket, they have small holes, or sometimes I've even seen for racing configurations, small balls that will help block fuel from exiting the basket region to help make sure that the basket, or in this main section, is filled with fuel. One of the additional advantages of this type of system is that we have the fuel pump itself inside the fuel tank. You might wonder, why is that a trend, or why is it that it's always advantageous to get it back to the fuel as far as possible? In that you're trying to reduce the amount of inlet pressure drop that occurs at the pump. And one of the things you can do is reduce it all the way down to minimal, is being inside the tank itself. I also show the vent here, and it's kind of important. Obviously the vent system is a lot more complicated, especially on modern vehicle, as it's being distributed to a charcoal canister such that you can recover vapors as opposed to allowing them to evaporate into the atmosphere. But one of the things that's important to note is that the more restriction that you have on a vent, the lower that the available absolute pressure is available to the pump. Or in other words, that's more pressure drop that occurs in the system. And then another next source of pressure drop is the straining filter itself. The straining filter on this is really required to help increase the reliability of the system. Many times a straining filter isn't to the same degree or fineness that you would encounter in the post fuel pump filter, or the main filter that people are associating with the system. And the real reason is that they're trying to avoid an accumulation of the debris around the straining filter to help increase its life. And they determine a certain size of a filter that may be required, such that debris that is at that size or smaller will generally not cause a problem for the pump, and it can continue to pump and push that debris on. Whenever we look at the system from this perspective, the main ideas that they're trying to accomplish is the ability to scavenge the fuel or remove the air going into the system, and also to help reduce the amount of inlet pressure drop effects to the pump to help avoid cavitation. I touched a little bit about cavitation on pumps in that last episode. However, it's important to note that it's a function of temperature and pressure. And when I say pressure, I mean in absolute terms. As you know, and right now we have about 14.7 psi of atmospheric pressure acting on us. And that is the available pressure that is possible to this first pump. And in that, any type of pressure drop, including the vent and the inlet straining filter, will reduce that amount of available absolute pressure to the pump inlet. I found this graph from the engineering toolbox that has a good representation of what's happening to the fluid as it goes through the pumping system. And here we have the P sub S, or the suction pressure, and that is the pressure that I was talking about at the inlet of the fuel pump. And we can see that it dips down, and that is because the pump has to draw fluid inside of itself, and it causes more vacuum or suction to be created. And this dips off the absolute pressure that's available on the fluid. And on the top graph here, we can show that as the pressure dips down, as long as we're above the vapor pressure, or the pressure which the fuel will boil, no cavitation will occur, and we can see that it makes it all the way out of the pump and into the discharge pressure, P sub D. And what can happen for cavitation, as they show in the bottom graph, is that this dip can occur below the vapor pressure. And what happens in that condition is that small bubbles of vapor form in the pump. Now, the formation of these bubbles are benign to the pump. The problem occurs is that once you get above the vapor pressure and start heading to the discharge pressure, what can happen is that these bubbles can collapse, and during the collapse is that they can cause damage to the system. That's why you'll see, generally speaking, the damage or the pitting occur at the pump outlet. And it's important to note that that vapor pressure line is the function of not only of the fluid, but also of what temperature. So as you raise the temperature, that vapor pressure line will start to raise. And if it raises up into the bubble formation, that's when you can get in trouble. And it should be important to note that it's not so much that the vapor is being created, but the problem is when that fluid with the vapor in there gets above that vapor pressure and starts heading to the discharge pressure, the bubbles can collapse, and that's where you can see damage caused by these collapsing bubbles. And that's why you kind of see it as a pitting or a destruction along the pump path. A long time ago, I created a test setup to test cavitation on a fuel pump, and here's a diagram of what that looked like. Here I can show what this pressure reference line, it was kind of unique, where I tied that with a fully sealed regulator, tied that back to the inlet pressure, and that had the effect of keeping the head pressure of the fuel pump constant. And I had the pump operating at maximum pressure. As I would restrict the inlet, this automatically altered the outlet pressure. And this had the effect of maintaining still a continuous head pressure and had a continuous flow rate as I started restricting the inlet. And while monitoring the inlet pressure, I restricted the inlet and got it right up to the point of cavitation. In fact, I just barely tapped it, and you can hear cavitation occurring, and I was able to notice a drop in flow rate. I probably had it less than a second in the cavitation mode, and went ahead and took apart the fuel pump and found permanent marks that were placed on the rollers themselves, the pump, and it's quite remarkable. But I started thinking about it, looking at that dip, and that would be that lower pressure that I've measured. That would be the equivalent of bringing that pressure down into that cavitation where that dip hit right at the vapor pressure. And with that data, if you compare it to maybe taking the exact same test fluid, putting a vacuum on it until it actually does boil, and then you can note those two different pressures, and that can give you a value for how much dip that you have of a given fuel pump. And I think that'd be a really interesting test setup. It'd be a lot harder to deal with applying a vacuum to, let's say, the reservoir if you wanted to do an in-tank pump. But the principle's the same. But that can give you an accurate way of comparing different fuel pumps in their susceptibility to cavitation. Now I can take a guess at which types of pumps may be better at resistance and cavitation versus others. And I would probably point towards, as a guess, would be probably turbine pumps and maybe even the screw pumps, having probably the least amount of shock or change in that pressure dynamic. As we see in the graph, I'll pull it back up again, that it's a very smooth curve for a centrifugal or turbine pump, and that would probably have the greatest resistance to cavitation. But again, who makes the pump and how it's configured, how the inlet's configured. Because if you have a turbine pump that has an extremely small inlet and you're trying to get 450 GPH out of it, or liters per hour out of it, then it's probably going to simply lower that or increase the dip in there. But maybe sometime we'll explore and how to make a test stand that tests this dip in the pumps themselves. But great care would have to be taken, as very slight amounts of cavitation can result in damage to the pump itself. It's almost a destructive test in itself. But if it handled it correctly and just barely tap it, more than likely it won't damage the pump permanently. Although I did see stripes, but the performance of the pump never changed after I ran that test for it. Let's get out of the weeds of cavitation and get back to scavenging really quick. We wanted to talk about different types of pumps. Here's a list of several different types of fuel pumps that I've seen used. I have an asterisk next to these types of pumps, the gear rotor, gear style, the roller and sling vane styles. A lot of times they're very similar in, I would say, pumping efficiency regarding the ability to pump gas. That's really what we're talking about as far as scavenging. I would also like to note too that turbine pumps are used quite a bit in scavenging. However, one of the things about the turbine pump is that they generally will have them right inside the fuel that's itself, and this allows it to get air out of the system a lot easier, such that the liquid would be much more readily available. And that's generally why you not see a turbine pump used for an external pump, just because the ability of a turbine pump to pump air or vapors is very diminished when compared to the other positive displacement pumps shown. I'd also like to get back to the Roadkill fuel pump failure. One of the things I didn't note was that when they did switch to the pump, I have to assume that that pump was still dead and still was not operating for them. I would really characterize that there's a couple possibilities that probably happened to it. I would say that debris could have gotten lodged in that first pump that they had, or that actually it suffered a catastrophic failure in on itself. It'd be really hard to believe that the latter, but it's possible. Perhaps the manufacturing of it wasn't quite to spec, or something was going on with the design. One of the things I would note was that the pump was a new design. However, it would really come down to, was a straining filter used or not. And if a straining filter was not used when he did the modification for the pickup system, then more likely than not that debris caused the failure. For this outro, I wanted to discuss, we talked a lot about cavitation, and I had a customer one time that had a problem during launch, and every time he launched, and it created a quick dip in the pressure at the inlet, he actually experienced momentary cavitation. And of course, during cavitation, as we talk about the vapors going through the pump assembly itself, quite often you're going to lose efficiency of that pump, and you're going to have a drop off on fuel capacity. And that's what he was experiencing. We're really kind of scratching our head, but in the end, he changed the inlet configuration of the fuel pump, and everything sorted back out again. But I think it's kind of important to note how quick cavitation could occur. When you're at a function of pressure, as soon as you hit that line of the vapor pressure, it will cavitate, and the cavitation can occur quite quickly. A lot of times when we're talking about boiling water and going, well, it takes a long time to boil this water, what's going on? Maybe some bubbles form as everything's heating up. But you got to keep in mind that is when you're raising the temperature up to, or the fluid up to the point of boiling. And that can appear to be a very slow process. It's a little hard to understand that temperature variations during the boiling process, as you're boiling water, for example, can often take a while, as different parts of the fluid are very different temperatures. The pot itself is usually a lot warmer, and heat transfer takes a while. So that's why it kind of gets to be an association that this is a phenomenon that would take a while to occur. But again, it can be instant and show its face. So I was actually a little bit surprised at that, but once that customer, we figured out what was going on, it did make sense, and that kind of fixed his problem. Anytime you're having a cavitation issue with a fuel system, for one, once cavitation occurs, it damages the fuel pump, and it needs to be replaced or rebuilt at that point. But in order to fix it, the best places to look for is reducing what the inlet, reducing the amount of pressure drop the inlet experiences. The other thing too is that heat plays an important role. Oftentimes, when cavitation occurs, it's usually after driving for a while, that when everything warms up. And again, it depends on how your fuel rails are mounted. If you do have cavitation, observe how hot the fuel is getting. The hottest part of the fuel system is on the return line, so look at that. Is that getting warm? Is it hot to the touch? If it is, it's likely that you're getting heat introduced into the system. And I would always look at the fuel rails. That's probably the fastest, really the greatest amount of heat that can get in there, basically because it's mounted not only so close to the engine, but a lot of time it's bolted directly up to the intake manifold or other sources of heat. I have seen people addressing that on the internet for some time. For example, Radium Engineering, I've seen that they had Ultim spacers and stuff like that to serve as insulators to prevent heat from getting into the rails, and that's a good place to start for all of that. I hope this video helps, and please like and subscribe and share it with others, and we'll be back. Thanks.